where curiosity floats like a feather on a quiet breeze, and science takes the scenic route towards slumber. Tonight, we set sail on a gentle journey far beyond our little blue planet, into the vast dark canvas above, a place where stars sparkle like ancient campfires, and somewhere in the quiet spaces between them, new worlds are born, planets like ours, like others we may never see, spinning, drifting, growing from cosmic dust into magnificent orbs that circle their suns. Have you ever gazed up at the night sky and wondered how it all began? How something as grand as a planet can grow from nothing but stardust and silence? And as you're listening tonight, wherever you are, what time is it in your little corner of the universe? Midnight? Early dawn? Or somewhere in between? If you find this peaceful little exploration soothing, if it helps you wind down after the long day's orbit, I would be ever so grateful if you gently pressed like or subscribed. It helps this small, quiet corner of the cosmos reach others who might need a little calm. Now, I do hope this won't be so fascinating that it keeps you awake, but if it does, well, at least you'll have wandered for a while among the stars before sleep arrives. So settle in, slow your thoughts, breathe easy, and let's begin. Because somewhere, in the hush between galaxies, a new world is forming. Have you ever noticed how certain places feel larger than life when you're young? How your childhood backyard seemed like an entire wilderness, or how a simple patch of sky could feel like an infinite ocean? And yet, as we grow older, those same places seem to shrink. The sky remains as wide as ever, the stars still twinkle from unimaginable distances, but somehow they feel a little smaller, a little closer, a little more ordinary. Our perception of space, much like our perception of time, is wonderfully elastic. It bends to emotion, to memory, to attention, and in many ways our minds experience the vastness of the cosmos not as something distant and unreachable, but as something intimate, woven into our stories, our dreams, and the quiet moments we spend looking up. When you look up at the stars on a clear night, you're not really seeing space in the clinical, scientific sense. You're seeing a canvas of possibilities, of ancient light carrying the whispers of distant fires. You're witnessing the slow, patient work of the universe unfolding, though your eyes only catch a frozen snapshot of its dance. To us, stars are steady. They twinkle gently. They seem timeless, almost eternal. Planets, too, feel permanent. They sit calmly in their orbits, circling their suns like loyal companions, as though they have always been there. Perfect, finished, complete. But of course they haven't. No planet was always a planet. Once, even Earth, with all its forests, its oceans, its cities full of glowing windows, was nothing but scattered dust and gas, floating aimlessly through a cold, dark void. Before Earth was Earth, it was a drifting cloud, a ghost of what it would someday become. And yet, when we try to picture how something like a planet might be born, our imaginations tend to reach for grand, sudden events, a mighty explosion, or a divine spark, or some fantastic cosmic machine assembling a world piece by piece. The reality, as usual, is far more patient, and somehow far more beautiful. In many ways, the birth of a planet feels a bit like the birth of a thought, slowly gathering, forming shape out of scattered ideas, pulling pieces together until something whole emerges. You may not notice the exact moment a thought is born, but over time it becomes real, solid, tangible, and so it is with planets. When you stare at the stars, you're looking at a sky filled with futures waiting to happen. Some of the pinpoints of light you see are already surrounded by planets, perhaps with their own moons, oceans, or clouds. Others may still be in the process of becoming, their dust clouds swirling silently, whispering promises of worlds yet to be. There's something deeply human about this cosmic process. the way we grow, the way our lives take shape, it mirrors the universe in its own quiet way. We begin as scattered cells, microscopic and fragile. Over time, gravity, or perhaps something like it, and pulls us together, piece by piece, experience by experience. We gather memories like dust grains. We collect hopes, disappointments, lessons, laughter. And slowly, without even noticing, we become something whole, a person, a self. In that sense, perhaps we're not so different from planets. Both of us born from scattered beginnings, both shaped by invisible forces pulling us toward form. And yet, while we live our lives on the cozy surface of one particular world, it's easy to forget that planets are still being born right now, all across the universe. Right this very moment, somewhere far beyond our sight, clouds of gas and dust are collapsing inward. Tiny grains are colliding, sticking, merging, growing. Worlds are taking shape, silently, slowly, waiting for their time to shine. If you listen closely, you can almost hear it. A gentle hush in the stars, the patient breath of creation. It's a curious thing, isn't it? How something so grand, the formation of an entire planet, can happen without fanfare, without trumpets or fireworks. Just the quiet work of gravity, of dust, of time. And yet somehow, knowing that makes it feel even more magical, as if the universe itself is a careful artist, patiently sculpting worlds from the simplest ingredients. You see, when we imagine the birth of a planet, our human minds crave drama. We picture fiery volcanoes, violent collisions, swirling chaos, and sometimes, yes, those things do happen. But the real miracle lies not in the violence, but in the balance, the patient harmony that allows scattered chaos to become ordered beauty. When we gaze up at the stars, we're not just seeing distant suns, we're seeing the faint, ancient glow of countless origin stories, each one different, each one unfolding at its own pace, each one a quiet reminder that even in the vast emptiness of space, there is always the gentle pull toward creation. And perhaps that's why we feel a certain comfort under the night sky, as though somehow we belong to that story, as though the same quiet forces that sculpted the planets are still at work in us, gently shaping, gently pulling, gently becoming. So the next time you find yourself staring up at the stars feeling small, remember, you're not small because you are insignificant. You're small because you are part of something vast. And in that vastness, you're exactly where you belong. A quiet participant in a story that began long before you and will continue long after. A story written in dust, in gravity, in time, and in the gentle hush of a planet being born. Long before telescopes, before rockets, before equations and simulations, humans looked up at the stars and saw stories. For our distant ancestors, the sky was not a cold, silent void. It was alive. It was a theatre of gods, of spirits, of signs, and the planets, those rare wandering stars that moved differently than the fixed constellations, were some of the most mysterious actors in that grand celestial play. We've been watching the planets for as long as we've had eyes to look up. The ancient Babylonians, over 4,000 years ago, were among the first to carefully track the movements of the planets across the night sky. They noticed that, unlike the fixed stars, these strange lights wandered back and forth in complicated patterns. They called them mulmul, the stars that do not rest. To them, these movements weren't random. They were messages, omens, signs from the gods about the fate of kings and empires. In fact, the very word planet comes from the Greek planets, meaning wanderer, because that's what they appeared to be, bright wanderers moving against the steady backdrop of stars. Different cultures would fill in the blanks with their own mythologies. To the Greeks, the planets were gods themselves. Mercury was Hermes, the fleet-footed messenger. Venus was Aphrodite, the goddess of love and beauty. Mars was Ares, the god of war. Jupiter, king of the gods. Saturn, ruler of time. Each one carrying not only a name but a personality. a divine essence that explained their presence in the heavens. In ancient India, the Navagraha, 9 celestial influences, held sway over destiny. Their mythology wove planets into an intricate web of karma, balance, and cosmic justice. These wandering bodies were seen as both guides and judges, reflecting the consequences of human actions and the rhythms of universal order. The Maya, too, tracked the planets with stunning precision. Their calendars could predict the cycles of Venus with breathtaking accuracy, down to the day. To them, Venus was not just a bright light, but a warrior god whose rise and fall signaled times for battle and ritual. In Polynesian traditions, the stars and planets were navigational companions, guiding sailors across thousands of miles of open ocean. The night sky was not a mystery, it was a map. A trusted partner whispering directions through subtle shifts in light and motion. And for the Norse, the sky held the great world tree, Yggdrasil, whose branches reached into the heavens, whose roots touched the underworld, binding all things together, including the celestial wanderers that grace the northern skies. Across continents and centuries, these drifting points of light inspired awe, fear, reverence, and comfort. Before they were objects of science, they were objects of meaning, and perhaps in a way they still are, because even now, after all the measurements, after all the high-powered telescopes and robotic missions, we still name new planets with a kind of quiet poetry. We name them after gods, after myths, after long-forgotten stories. We can map their orbits with precision, calculate their mass, simulate their formation, but we still whisper their names with a touch of wonder. The human urge to find stories in the sky runs deep, and perhaps that's because the sky offers something we rarely find on Earth: permanence. Down here, rivers flood, mountains crumble, cities rise and fall. But the stars, the planets, they return, season after season, generation after generation. They are ancient companions. They remind us that while our lives are brief flickers, the universe keeps its slow, steady rhythm. Even our word cosmos comes from the Greek kosmos, meaning order. To early astronomers, the sky wasn't chaotic. It was beautifully arranged. The planets' movements, while mysterious, hinted at some deeper pattern, a cosmic clock ticking away with precision. Of course, for most of history we misunderstood that clock. For centuries the prevailing view was that Earth sat at the centre of it all. The stars, the planets, the sun, all circling us in nested crystal spheres, perfectly arranged. This geocentric model wasn't just a scientific theory, it was a worldview. It placed humans at the heart of creation, under the watchful eyes of gods and stars alike. But even within this mistaken model, ancient astronomers noticed something strange about the planets. Occasionally they seemed to move backward in the sky, a puzzling phenomenon called retrograde motion. Mars, for instance, would appear to slow down, reverse course, and then continue forward again. This baffling dance led to elaborate models full of epicycles, smaller circles within larger circles, to explain the wandering paths. It wasn't until the 16th century that Nicholas Copernicus gently upended this view. He proposed something both radical and beautifully simple. Perhaps the sun, not Earth, was at the centre. Suddenly the odd backwards loops of the planets made sense. They weren't reversing course at all. We were simply watching their orbits from our own moving vantage point. Galileo Galilei, with his newly built telescope, would soon provide evidence that shook the old cosmic order. He saw the moons of Jupiter circling their parent planet, proving that not everything revolved around Earth. He saw the phases of Venus, matching the predictions of a sun-centered system. The planets were not gods, they were worlds. That shift, from celestial omens to celestial objects, marked a profound turning point in our relationship with the cosmos. For the first time, planets weren't just symbols, they were places, real places, perhaps even places like our own. And yet, Even as science pulled back the curtain, the wonder remained, because with every question answered, new mysteries emerged. How were these planets born? What forces sculpted them from the dust of ancient stars? Could there be others, far beyond our own sun? As our instruments grew more powerful, we discovered that our solar system was not unique. In 1995, astronomers discovered the first confirmed exoplanet, a world orbiting a star far beyond our sun. Since then, thousands more have been found, each one a new thread in the grand cosmic tapestry. Some of these exoplanets are gas giants larger than Jupiter, hugging their stars in tight, blistering orbits. Others are small, rocky worlds like Earth, drifting through the habitable zone where liquid water might exist. Some orbit twin suns like distant Tatooines. Others roam alone, untethered to any star, a lonely existence in the cold dark. And with each discovery, our ancient myths find echoes in modern science. The wanderers still wander. The stories still unfold. Different cultures have seen the planets as gods, as signs, as guides. And now we see them as worlds being born, living, evolving, drifting through time and space in a cosmic ballet that has played out for billions of years. But even now, our scientific understanding is still wrapped in language that reflects our oldest instincts. We speak of birth when describing planetary formation, of migration when planets shift their orbits, of death when stars swell and consume their children. The language of life permeates our study of the stars, as if we cannot help but see in the heavens a reflection of ourselves. And perhaps that's the truest legacy of our long, tangled relationship with the planets. Whether as gods or gas giants, omens or orbits, symbols or spheres, the planets have always been our mirrors, silent reminders of both how small we are and how vast we belong. As you listen tonight, you might imagine yourself standing beside one of our earliest ancestors thousands of years ago, looking up at a sky free from city lights, the stars blazing in impossible numbers, the planets gliding slowly across the black canvas. You might imagine their whispered questions, the same ones we still ask. Where did it all come from? What does it mean? What is my place beneath this sky? In the end, across all cultures, all histories, all beliefs, perhaps the planets have always offered us the same quiet comfort. The knowledge that the universe is ancient, patient, and still unfolding, and that somewhere, far away, new worlds are being born even now, drifting through the stars. So far we've drifted gently through the ancient stories and human wonder that have swirled around the planets for millennia. But now, let's pull back the curtain just a little further and peer into the quiet workings of the cosmos itself. Because while the ancients saw divine wanderers in the sky, we've since learned that planets are not born by magic, but by an astonishingly patient process of dust, gas, gravity, and time. In the beginning, there is only a cloud, a vast cold cloud of gas and dust drifting aimlessly through the great emptiness between stars. These clouds have a name, molecular clouds, or sometimes more poetically stellar nurseries. They are unimaginably large, some stretching for dozens, even hundreds of light years, and within them lie the raw ingredients for stars, planets, and everything in between. The dust within these clouds isn't like the dust that gathers beneath your couch, though perhaps both are equally mysterious. This cosmic dust is made of tiny grains of rock, ice, metals, and complex molecules. It's the leftover material from earlier generations of stars. Stars that once burned brightly, lived out their lives, and then exploded, scattering their enriched ashes back into space. You could say that planets, and even you and I, are born from the recycled remnants of ancient stars. As the old saying goes, we are made of star stuff. But a cloud doesn't spontaneously become a planet, it takes a nudge. That nudge might come from many things: the shockwave of a nearby supernova, the gentle tug of galactic gravity, or the collision of smaller clouds merging together. Whatever the cause, a ripple of disturbance travels through the cloud, causing regions of higher density to form. In these denser pockets, gravity begins its slow, inevitable work. Particles of dust and gas are drawn together, like raindrops gathering into a puddle. The more material they attract, the stronger their gravity becomes, pulling in even more. This runaway process is called gravitational collapse. At the heart of each collapsing region, temperatures rise, pressures build, and eventually, after millions of years, a star ignites. But around that new star, the story of planets begins. Surrounding the newborn star is a swirling, spinning disk of leftover material, gas, dust, and debris, like the aftermath of a grand celestial construction project. This is called a protoplanetary disk. It's here, in this thin, glowing ring of debris, that planets are born. But the disk doesn't immediately form neatly organized worlds. No, at first it's chaos. Tiny dust grains collide gently, sticking together through weak electrostatic forces, a process known as coagulation. Think of it like cosmic static cling. Dust bunnies in space, growing larger as more grains collect. Over thousands of years, these clumps grow into pebbles, then rocks, then larger objects called planetesimals, essentially baby planets, ranging in size from a few meters to hundreds of kilometers across. At this stage, collisions become more dramatic. Some planetesimals shatter, breaking apart into smaller pieces. Others stick together, merging into even larger bodies. This competitive process is known as accretion, a word that simply means to grow by gathering. Gravity, once again, is the silent architect. As planetesimals grow larger, their gravitational pull increases, allowing them to attract more material from the surrounding disk. Over millions of years, these growing worlds sweep through their orbits, clearing paths in the disk, hoarding material like cosmic vacuum cleaners. This phase of violent mergers, collisions, and growth is often called the giant impact stage, and it can be rather dramatic. Our own Earth likely experienced one of the most famous collisions in planetary history. In its youth, Earth is thought to have collided with a Mars-sized object, often called Theia. The impact was catastrophic, vaporizing parts of both bodies and throwing molten debris into orbit. Over time, that debris coalesced to form our Moon, a silent witness to the violence of our planet's earliest days. But not all planets are born the same way. The distance from the star plays a crucial role in determining a planet's destiny. In the inner regions of the disk, close to the heat of the newborn star, temperatures are too high for most gases to condense. Only heavy materials like metals and rock can survive here. That's why the inner planets of our solar system, Mercury, Venus, Earth, and Mars, are small, rocky worlds. Farther out, beyond what's known as the frost line, temperatures drop. Here, lighter gases like hydrogen, helium, methane, and ammonia can condense into ices. This allows for the formation of much larger planetary cores, which then attract vast envelopes of gas, becoming gas giants like Jupiter and Saturn, or ice giants like Uranus and Neptune. The diversity of planets, rocky, gaseous, icy, all stems from this simple difference in distance and temperature. Yet, even this neat division is not always so neat. In other solar systems, we've found gas giants orbiting scorchingly close to their stars, so-called hot Jupiters, giant planets where we never expected to find them. Their existence challenged our theories and forced us to realize that planetary formation isn't always as tidy as our own backyard suggests. How did these hot Jupiters get there? One possible answer: planetary migration. You see, once formed, planets don't always stay where they were born. As they interact with the gas and dust in the disk, or with other planets, gravitational forces can nudge them inward or outward, shifting their orbits dramatically. Some may fall into their stars and vanish. Others may be flung outward into distant icy orbits. Some may even be ejected entirely, becoming rogue planets, wandering the interstellar void alone, unbound to any sun. It's a wild, dynamic, unpredictable dance. A cosmic pinball machine that continues for millions of years, sculpting the final architecture of a planetary system. And yet, through all this chaos, order eventually emerges. The gas dissipates, the debris clears, the collisions slow. What's left behind are stable, well-behaved worlds, each locked into its orbit, circling its star in quiet harmony. Our own solar system is the result of billions of years of this invisible sculpting, a delicate arrangement of 8 major planets, dozens of moons, countless asteroids and icy comets, all born from the same ancient cloud. And perhaps most remarkable of all, this entire process, from swirling dust to shining worlds, is not rare. The more we look, the more we find. Thousands of exoplanets have already been discovered. Some orbit 2 stars. Some are locked in eternal days or frozen nights. Some may even harbour liquid water, or perhaps life. And somewhere out there, even now, in the quiet reaches of the galaxy, more planets are being born, slowly, patiently, invisibly. The universe never rushes. If the story ended there, with a neatly arranged system of planets, it would already be wondrous enough. But even after a planetary system settles into its final shape, the work of building a planet is far from finished. Because now comes a quieter, slower phase, the long cooling. Planets fresh from formation are hot, sometimes glowing with the leftover heat of their violent assembly. Over time, this heat dissipates, leaking slowly into space. The planet's surface cools, hardens and reshapes itself. Mountains rise, valleys deepen, oceans may gather in craters and basins if conditions allow. Atmospheres begin to form or are stripped away. Each world becomes its own small laboratory, sculpted by its own unique mix of ingredients, position and history. Some planets remain dry and barren, locked in silent solitude. Others, like Earth, strike a rare balance that allows liquid water to pool, and perhaps life to take hold. Even tiny variations can lead to wildly different outcomes. Take Venus, for example. Similar in size and composition to Earth, yet utterly inhospitable. Its atmosphere, thick with carbon dioxide, traps heat in a runaway greenhouse effect, raising surface temperatures hot enough to melt lead. Its clouds rain sulfuric acid. No peaceful sunsets there, just a broiling toxic furnace. Or consider Mars, cold, dry, dusty. Evidence suggests that it once had flowing rivers, lakes, and perhaps even oceans. But today, its thin atmosphere offers little protection from radiation or cold. What happened? Was it simply too small to hold on to its atmosphere? Was its magnetic field too weak? We're still piecing together the story. And then, of course, there's Earth. Somehow, against astonishing odds, falling into just the right Goldilocks zone. Not too hot, not too cold. Protected by a magnetic field that shields us from solar radiation. Stabilized by a large moon that steadies our rotation. Enriched by a delicate atmosphere that sustains life as we know it. So many tiny factors, all conspiring or cooperating to create a world where oceans roll, forests breathe, and creatures like you and I gaze up at the sky, asking how it all began. And yet, Earth's story is far from unique. Across the galaxy, as we peer deeper into the darkness, we see tantalizing hints of planets that might be just as hospitable, or perhaps far stranger. Some exoplanets orbit in tidally locked orbits, forever presenting the same face to their star. One side baked in perpetual daylight, the other frozen in endless night. The narrow strip between these extremes, a twilight ring circling the planet, might be the only habitable zone. Others may orbit red dwarfs, tiny dim stars that burn for trillions of years, far longer than our sun. Their planets, if protected from stellar flares, could offer stable environments for eons, far longer than Earth may ever know. And then there are super-Earths, rocky planets larger than our own, with stronger gravity, thicker atmospheres, and unknown potential for habitability. Each new discovery nudges our imaginations wider, and yet for all the variety, the underlying process remains surprisingly universal. A cloud collapses, a star ignites, a disk forms, dust gathers, collisions build worlds, orbits stabilize, worlds cool and evolve. The universe, vast as it is, seems to follow this same quiet rhythm, endlessly repeating variations on the theme of creation. But even this elegant model leaves room for mysteries. For example, why do some systems produce only 1 or 2 planets, while others form dozens? Why do some gas giants end up close to their stars, while others linger in cold, distant orbits? Why do some systems remain stable for billions of years, while others collapse into chaos? We're still learning. One emerging idea is that the birth environment itself matters. The density of the molecular cloud, the turbulence of the gas, the magnetic fields at play, the presence of nearby stars whose gravity or radiation can disrupt the disk. Even small variations at the beginning can dramatically reshape the outcome. It's like baking. The ingredients may be familiar, but the slightest change in temperature, moisture, or timing can produce something entirely new. The universe, it seems, is a master baker, endlessly experimenting with its cosmic recipes. And then there are the planetary systems that defy our expectations entirely. Systems with tightly packed orbits, where multiple planets circle their star in near-perfect resonance, like synchronized dancers gliding across a ballroom floor. Or systems where planets share the same orbit, known as co-orbital planets, gravitationally balanced in a delicate cosmic waltz. And always, just beyond our current reach, the next mystery waits. Even as we discover thousands of exoplanets, we've only just begun to glimpse their surfaces, their atmospheres, their potential to host life. Telescopes like the James Webb Space Telescope are now peering into these distant worlds, analyzing the faint starlight that passes through their atmospheres, searching for the telltale signs of water vapor, oxygen, methane, or even the complex molecules that might hint at biological activity. We stand today on the very edge of a new era of planetary science, one that may soon reveal not just how planets are born, but how many might be capable of hosting life. And perhaps, someday, we may even glimpse another world like our own, another blue marble spinning quietly in its own corner of the sky, a distant cousin waiting to be discovered. But even if we never find another Earth, the very fact that planets exist at all, born from dust, shaped by gravity, cooled by time, is enough to fill the heart with wonder. Because every planet, no matter how alien, began the same way, with a quiet cloud, with a patient pull, with the hush of ancient stardust, gathering itself into something new. And somewhere, even now, in a stellar nursery far beyond our sight, another world is beginning its long, silent drift toward becoming. So far, we've floated gently through the broad story of how planets form, from scattered clouds to swirling disks to emerging worlds. But as with many things in nature, the closer we look, the more intricate and strange the picture becomes. Because the universe, while patient, is never simple. The process of building a planet is not just one long, smooth road, but a series of stages, complications, and cosmic balancing acts. So let's slow down for a moment and step a little closer into the details, the mechanisms, the delicate choreography. Because even in the calm, there is complexity. At the very beginning, the raw material of planet formation is unimaginably tiny. Dust grains. Each grain might be just a few microns across, smaller than the width of a human hair. These tiny particles float aimlessly through the protoplanetary disk, jostled by the turbulent swirl of gas, buffeted by radiation from the young star, gently colliding with each other. But even these first steps are not as simple as they seem. When dust grains collide at very low speeds, they can stick together. Surface forces, like Van der Waals forces, allow them to cling, much like flour clumps when you bake. This leads to the slow formation of millimetre and centimetre-sized aggregates, the pebbles. And here, already, the first great mystery appears. We call it the metre-sized barrier. As pebbles grow into larger bodies, they face a problem. The drag from the surrounding gas, which is still thick and turbulent, starts to pull these objects inward toward the star. Essentially, mid-sized bodies spiral inward and risk falling into the sun before they can grow into anything substantial. This has puzzled scientists for decades. How do these early building blocks avoid this doom and continue growing? One likely answer is that pebble accretion plays a crucial role. In certain regions of the disk, small pebbles may become concentrated into dense clumps by instabilities in the gas itself, eddies, vortices, or regions of high pressure. These regions create safe harbours where particles gather, allowing gravity to take over. In these zones, larger objects can rapidly sweep up pebbles, growing quickly enough to escape the inward pull toward the star. It's like an eddy in a river catching leaves, allowing them to pile up rather than wash downstream. And once these growing bodies pass a certain size threshold, around a kilometre or so, gravity begins to dominate. The planetesimals are born. The formation of planetesimals marks a turning point. No longer governed solely by gentle sticking, growth now becomes a game of gravity, speed and collision. Planetesimals orbit the star like tiny worlds in their own right. As they cross paths, they collide, sometimes merging, sometimes shattering, sometimes rebounding. Each encounter changes their paths, their speeds, their shapes. The larger a planetesimal becomes, the more effectively it can pull in nearby objects through a process called gravitational focusing. This leads to what scientists call runaway growth, where the biggest bodies grow faster, sweeping up material more efficiently than their smaller neighbours. It's a bit like a snowball rolling downhill, gathering more snow as it grows heavier and larger. But this phase is not peaceful. High-speed collisions between planetesimals can sometimes be catastrophic, breaking them apart into clouds of debris. Some fragments reassemble, while others are lost forever. In this way, the early disk becomes a violent arena of merging and destruction, a celestial demolition derby lasting millions of years. And yet, out of this chaos, a few survivors emerge, the planetary embryos. At this stage, a planetary system is starting to take shape. But depending on where a planetary embryo finds itself within the disk, its future may look very different. Closer to the star, inside the frost line, temperatures remain too high for volatile compounds like water, methane, or ammonia to condense. Here, rocky materials dominate, leading to the formation of terrestrial planets. Small, dense, and rocky, like Mercury, Venus, Earth, and Mars. Farther out, beyond the frost line, ices are abundant. This allows embryos to grow much larger, much faster, as they accrete not only rock but also frozen gases. If an embryo becomes massive enough, typically about 10 times the mass of Earth, it can begin pulling in vast amounts of hydrogen and helium from the surrounding gas. This is how gas giants are born. Jupiter, for example, likely started as a rocky icy core, rapidly ballooning as it attracted gas from the disk, becoming the massive world we know today. Saturn followed a similar path. Farther out, Uranus and Neptune likely formed cores too, but collected less gas, becoming ice giants instead. But this process is exquisitely sensitive to timing. The gas in a protoplanetary disk doesn't last forever. Within a few million years, the young star's radiation blows much of it away. Any planet that hasn't grown large enough by then loses its chance to become a gas giant. In this way, planetary formation becomes a kind of race. Who can grow fast enough before the gas is gone? Even after planets form, their positions may not be final. The early disk is still full of gas and debris, and this material can exert forces on the planets, nudging them inward or outward over time. This process, planetary migration, helps explain some of the strangest systems we've discovered. hot Jupiters orbiting dangerously close to their stars, or tightly packed chains of planets in near-resonant orbits. In some cases, multiple planets may interact gravitationally, altering each other's orbits in complex ways. Some may be flung out entirely, becoming rogue planets, wandering the galaxy alone. Others may settle into long-term stability, their chaotic youth giving way to quiet orbits. Even our own solar system likely experienced migration. Models suggest that Jupiter and Saturn may have moved inward and then outward again, dramatically reshaping the orbits of the smaller planets and scattering icy bodies outward to form the Kuiper Belt and Oort cloud. Without these migrations, Earth itself may never have formed as it did. Even after the major planets settle into stable orbits, the story of collisions isn't quite over. In our own solar system, about 3.9 billion years ago, a final chaotic episode unfolded, the Late Heavy Bombardment. During this period, leftover planetesimals and asteroids rained down on the inner planets, scarring their surfaces with countless craters. The Moon, Mars, Mercury, even Earth, all bear the marks of this violent era. Some scientists believe this bombardment may have delivered water and organic molecules to Earth, the seeds, perhaps, for the emergence of life. In this way, even the destruction of early collisions may have played a quiet role in fostering life's beginnings. And yet, even after billions of years, the process of planetary formation still isn't entirely complete. Debris continues to circulate. Asteroids occasionally strike planets. Moons are still being reshaped by tides. Rings are being sculpted by gravitational shepherds. The cosmic construction site never truly closes. Even now, our solar system hums with quiet motion, as it has for billions of years. And somewhere, in another protoplanetary disk far away, these same strange, delicate processes are unfolding once again, as they have for eons, as they will for eons more. As we peer deeper into the process of planetary birth, we start to realize that even after the wild collisions, migrations and bombardments, the quiet work of shaping a planet is far from over. Because once a planet survives its youth and finds a stable orbit, another phase begins, a long, patient transformation that slowly refines its character over billions of years. A young planet, freshly cooled, is often restless inside. The heat from its formation, combined with radioactive decay within its core, keeps its interior churning. This internal heat drives geological processes. Volcanoes erupt, continents drift, mountains rise and crumble. The surface, far from static, is constantly reshaped. On Earth, the slow motion of tectonic plates builds and destroys entire landscapes over immense stretches of time. This geological activity plays a crucial role in recycling carbon, regulating climate, and even supporting life. But geology is only part of the story. A planet's atmosphere, if it has one, adds its own layers of complexity. Early atmospheres are often dominated by light gases like hydrogen and helium, but these can easily escape into space, especially on smaller planets with weaker gravity. What remains or accumulates later, whether it's carbon dioxide, nitrogen, oxygen, or methane, depends on countless factors: volcanic activity, chemical reactions, impacts, and even the emergence of life itself. Take Earth's atmosphere, for instance. It wasn't always rich in oxygen. For the first 2 billion years, oxygen was virtually absent. It was only with the rise of photosynthetic organisms, tiny cyanobacteria living in ancient oceans, that oxygen began to accumulate. This slow, invisible transformation, known as the Great Oxygenation Event, dramatically altered the planet's chemistry and paved the way for complex life. Without those tiny microbes, there might never have been trees, birds, whales, or humans to gaze up at the sky and wonder where it all began. And yet, even that event was just one possible path among countless others. On some planets, life may never arise. On others, it may follow completely different courses shaped by entirely alien chemistries. Mars offers a sobering contrast. Once, it may have boasted rivers, lakes, even shallow seas, but lacking a strong magnetic field, its atmosphere was slowly stripped away by solar winds. Today it is cold, dry, and thin, a silent, frozen witness to its own lost potential. And yet, beneath its surface, there may still be secrets, frozen pockets of water, or even microbial life clinging stubbornly in hidden places. Venus tells a different cautionary tale. Similar in size to Earth, it likely had a more temperate beginning. But trapped in a runaway greenhouse effect, its surface grew unbearably hot, its clouds thick with sulfuric acid. The delicate balance tipped, and now Venus stands as a reminder of how fragile planetary habitability can be. A sister world, but an unrecognizable one. Even moons enter this grand narrative. Some, like Jupiter's Europa or Saturn's Enceladus, hide oceans beneath icy shells, warmed by internal heat and tidal flexing from their parent planets. These subsurface oceans may offer environments where life could exist, independent of sunlight, sustained by chemical energy alone. It's a strange thought that while we often search for habitable planets, some of the most promising homes for life might circle faraway giants in the frozen dark. And all of these diverse outcomes are sculpted by factors set in motion billions of years earlier, during those first silent moments in the swirling protoplanetary disk. The timing of collisions, the distances from the star, the strength of magnetic fields, the thickness of atmospheres, all ripple outward, determining a world's fate long before its story can even unfold. But while we've come to understand many of these mechanisms, vast questions remain. Why do some systems produce tightly packed clusters of small rocky planets, while others give rise to enormous gas giants on eccentric orbits? What roles do stellar winds, magnetic fields, and nearby stars play? How rare, truly, is a world like Earth, a place where complex life emerges and endures across billions of years? We're only beginning to glimpse the full variety of planetary systems scattered across the galaxy. Our telescopes, though powerful, can barely see the surfaces of these distant worlds. Much of what we know comes from shadows, tiny dips in a star's brightness as a planet crosses its face, or subtle wobbles in a star's motion as unseen planets tug gently at it from afar. From these faint signals we infer masses, sizes, orbits, and compositions. But the details, the landscapes, the clouds, the oceans or deserts, remain hidden for now. Yet even in these whispers, patterns begin to emerge. Some stars host systems of tightly packed super-Earths, orbiting close to their parent suns in perfect synchrony. Others boast immense gas giants, hugging their stars in orbits shorter than a single Earth week. Still others seem to lack planets entirely, barren and silent. There are planets with two suns, planets shrouded in permanent storms, planets larger than Jupiter but with densities lighter than cork, bloated by their heat into swollen, puffy spheres. There are rogue planets, cast adrift from their stars, wandering alone through interstellar space in perpetual night. And somewhere, perhaps, there are planets like ours, quietly nurturing their own forms of life under alien skies. The more we discover, the clearer it becomes that planet formation is not a single script, but a branching tree of possibilities, an intricate web of cause and effect, chance and necessity, played out across billions of years. The laws of physics set the stage, but the universe allows for infinite variations within those rules. And even as we marvel at this diversity, one simple truth remains. It all begins the same way. A quiet cloud, a slow collapse, a swirl of dust lit by a newborn star. And from that, over unimaginable spans of time arise oceans and mountains, storms and seasons, and perhaps even creatures who wonder where it all came from. Somewhere, far beyond the reach of our eyes, another star is kindling into life even now. Around it, a disk of gas and dust is beginning to spin. Tiny grains are colliding, clumping, merging. The quiet labour of creation has begun again. And billions of years from now, perhaps someone, somewhere, will gaze up at their own sky, beneath the light of that distant sun, and wonder, as we do, how their world came to be. The stars whisper their stories, patient and unhurried, and among those stories, the tale of how planets are born continues, as it always has, quietly drifting through the stars. Long before we could measure, calculate, or model how planets are born, we simply watched. The night sky offered a grand stage, and for much of human history, we sat quietly in the audience, gazing upward, wondering, imagining. And in that long prelude to scientific discovery, stories flourished. In the earliest days, there was no separation between the heavens and the divine. The planets, those few strange lights that wandered across the sky, were not merely objects. They were beings, gods, spirits, omens. Venus shone as a goddess of love, Mars as the bringer of war. Their movements were signs, their patterns carefully tracked by astrologers and priests. The Babylonians, over 4,000 years ago, kept meticulous records of planetary motions on clay tablets, not for scientific curiosity as we know it, but as a way to glimpse the intentions of the gods. For centuries, planets remained mysterious wanderers, their true nature hidden behind layers of mythology. And yet, even within those early observations, seeds of deeper understanding were quietly being planted. The Greeks, particularly thinkers like Ptolemy, began building models to predict planetary motion. His great work, the Almagest, described a complex system of epicycles, circles within circles, to explain the peculiar backward loops planets sometimes traced across the sky. This geocentric model placed Earth at the centre of everything, and for over 1,000 years it was accepted as the natural order of the cosmos. But as careful observation sharpened, the model's flaws became harder to ignore. The planets, in their stubborn wanderings, refused to perfectly obey the elegant circles Ptolemy described, and slowly, a quiet revolution began to stir. In the 16th century, Nicholas Copernicus proposed a radically different idea. What if Earth wasn't the centre? What if the Sun sat at the heart of the solar system, with Earth and the other planets orbiting it? This heliocentric model was simple, elegant, and deeply unsettling to a world that had long imagined itself at the centre of creation. Yet even Copernicus, cautious as he was, didn't fully grasp the implications of his own model. His circular orbit still didn't perfectly match the data. It would take another mind, Johannes Kepler, to sharpen the picture further. Kepler, working tirelessly with the detailed observations of Tycho Brahe, discovered that planets did not move in perfect circles but in ellipses, slightly stretched ovals, with the Sun at one focus. This small correction was profound. With Kepler's 3 laws of planetary motion, the clockwork of the solar system finally began to reveal its true rhythm. Not long after, Galileo Galilei, armed with one of the first telescopes, turned his gaze to the heavens and shattered even more ancient assumptions. He saw the phases of Venus, proving it orbited the Sun. He watched moons circling Jupiter, clear evidence that not everything revolved around Earth. He observed the rugged mountains of the Moon, the countless stars of the Milky Way, and the strange spots upon the Sun. The heavens, once believed to be perfect and unchanging, were now revealed as dynamic, imperfect, and full of structure. Galileo's observations confirmed that planets were not divine wanderers, but physical worlds, solid places, perhaps even places like our own. Then, in the 17th century, Isaac Newton brought it all together. With his law of universal gravitation, Newton described the force that held planets in their orbits and explained why they moved as Kepler had described. Gravity, he proposed, was a universal attraction between all masses, binding the moon to Earth, the planets to the sun, and the stars to each other across the vast reaches of space. For the first time, planetary motion wasn't a mystery. It was a predictable consequence of natural laws, elegantly expressed in a few mathematical equations. The orbits of the planets, the tides of the seas, and the fall of an apple were all part of the same grand unifying framework. And yet, while Newton could describe how planets moved, he could not yet explain how they came to be. For centuries after Newton, the question of planetary formation remained largely speculative. Some proposed that planets were formed from material ejected by the sun, or that they condensed from swirling cosmic vapours, but hard evidence was scarce. The birth of planets remained hidden behind the veil of deep time. It wasn't until the 20th century that real progress began. As astronomers turned their attention to the birthplaces of stars, those great molecular clouds and glowing nebulae, they realized that planets likely formed as natural byproducts of star formation itself. Observations of young stars surrounded by disks of dust and gas, the protoplanetary disks, offered the first real glimpses of the earliest stages of planetary birth. Simultaneously, advances in physics, particularly the study of fluid dynamics and thermodynamics, allowed scientists to begin modelling how such disks evolve. Theories emerged describing how tiny dust grains might stick together, how gravity might take over, how planetesimals might collide and grow, and slowly a coherent picture began to emerge. In the late 20th and early 21st centuries, the discovery of exoplanets, planets orbiting stars beyond our Sun, transformed the field completely. The first confirmed detection came in 1995, a gas giant orbiting a star called 51 Pegasi, shockingly close to its Sun. This hot Jupiter was unlike anything found in our own solar system, and its existence forced scientists to reconsider long-held assumptions about how planets form and migrate. Since then, thousands of exoplanets have been discovered, revealing an astonishing diversity of worlds. Super-Earths larger than our planet but smaller than Neptune, tightly packed systems of rocky planets orbiting red dwarfs, gas giants skimming the surfaces of their stars, rogue planets wandering alone between stars. Each discovery challenged and refined our understanding of planetary formation, revealing that the processes at work are both more universal and more varied than we ever imagined. While the basic physics, gravity, accretion, migration, remain consistent, the outcomes are shaped by an intricate web of initial conditions and complex interactions. At the same time, powerful telescopes like ALMA, the Atacama Large Millimeter, Submillimeter Array, have allowed us to peer directly into protoplanetary disks surrounding young stars, catching glimpses of planets in the act of forming. We can see dark gaps carved into the disks where young planets have already begun clearing their paths, shepherding material into rings and lanes, a cosmic signature of planetary birth unfolding before our eyes. The James Webb Space Telescope, launched in the 2020s, has pushed this vision even further. With its unprecedented sensitivity to infrared light, Webb allows us to study the chemistry of distant planetary atmospheres, the structure of young disks, and perhaps one day, the very ingredients that may give rise to life itself. And so, in just a few short centuries, we have journeyed from watching wandering stars with the naked eye to directly observing worlds being born in distant star systems. Yet, for all we have learned, the mystery remains as beautiful as ever. How many planets are out there waiting to be found? How many are Earth-like? How many host life? These questions still hang like stars in the dark, their answers waiting patiently in the silence of deep space. We now know that planetary formation is not some rare miracle, but a natural consequence of star birth, a quiet, ongoing process that has played out billions of times across the universe. The same forces that shaped our own Earth are at work in distant stellar nurseries even now, weaving new worlds from the dust of dead stars. And yet, even as we build models and gather data, we remain, at heart, the same curious creatures who first gazed up at those wandering lights so long ago. We still wonder, we still listen, we still drift through the stars, one question at a time. When we speak of planets being born, it is easy to become lost in the mechanics, the dust grains, the collisions, the swirling disks of gas. The equations can describe their orbits, the telescopes can glimpse their distant silhouettes, the models can simulate their formation with beautiful precision. But somewhere beneath all of that quiet mathematics, a stranger question hums. Why does anything form at all? Why, in the great silence of the universe, does dust not simply remain dust? Why does the emptiness not stay empty? Why instead does gravity gather matter into stars, into planets, into places? It seems so unlikely that out of a cloud of cold gas, entire worlds might one day emerge. Oceans, mountains, atmospheres, even creatures who gaze upward and wonder. But that perhaps is the heart of the mystery, that complexity seems to arise so naturally, again and again, from the simple. In a sense, planetary formation is not simply a physical process. It is also a kind of unfolding, like the petals of a flower opening in the sunlight. From the tiniest initial irregularities in a cloud of gas, entire solar systems bloom into being. And once they exist, their mere presence invites questions that no telescope can fully answer. Is this common? Is it rare? Are we a singular accident or one branch in an endless forest of life? The more we learn about planets, the more we see that the universe is very good at making them. They form readily. Their births are not extraordinary, but ordinary. The real mystery, then, is not how planets form, but what happens afterward. Out of all the planets born from swirling dust, how many evolve into places where rivers run, where storms